problem that we're facing with wind energy applications is that you're trying to place a turbine in the countryside somewhere and you want to know where is the best place for that turbine. And that's wonderfully easy when you've got nice, perfectly flat terrain, so places like the Netherlands, Germany are wonderful for that. But in this country we've got the problem that we've got undulating terrain, mountainous terrain, and when you place a turbine there, then the wind flow over the hill is not laminar, is not steady. And so depending on which direction the wind comes from, you can get strong turbulences, eddies, things affecting the wind turbine in a negative way. So you want to be very, very sure where you put your turbine, that that's really the best place to put it. And there are simulation models, weather models around that are attempting that, but they're not terribly good. They have spatial resolutions of a mile usually, so small structures like a hill of maybe 200, 300, 400 meters diameter won't be resolved by these projects. So the wind flow will be hard to forecast, and the best thing to do is go out there and measure. So what's currently done is they are putting masts, meteorological masts on a hill, and they're putting a thing called cup anemometers, little twirly things, rotating things that measure the wind. The trouble with these is you get them at one height, maybe at 3, 4 heights, and a mast can be typically maybe 30 meters high to be easy to set up. The trouble is that these wind turbines, modern wind turbines, are typically 70-meter hub height, so the blades can easily extend up to 120 meters high, and we've seen wind turbines, I think, that are up to 200 meters high with the greatest blade extension. So putting up a mast of 200 meters, or let's say 150 meters if that's a hub height, is a real task. Very, very hard to do, very expensive, and you can't just shift it from one place to the other to experimentally find out where the best place for that wind turbine will be.
We're using what's called a SODAR, which stands for Sound Detection and Ranging, and it's got a similar sounding name to radar, as you can hear, which uses rather than using radio waves, as radar does to detect the range and speed of objects. It uses sound. So sound waves are projected into the atmosphere and are actually reflected back off objects. So what we're using at the university is we'll have a large array of loudspeakers. There's 32 loudspeakers, all in a square 6x6 array, which is actually 36, but we're not using the corner speakers. And by having this large array of loudspeakers, you can actually do what's called a phased array, and you can actually direct the sound in different angles electronically. So you can fire a beam of sound at different angles and detect objects in different orientations.
What the wind turbine operator would like to do is they would like to put these instruments out there, measure for 2, 3, 4 months, and have 100% data availability, obviously, and have a really nice, fine spatial resolution in the vertical, and have very, very accurate results. So that would be the perfect world, and it's never going to work like that. No instrumentation can do that. All instrumentation fails in some weather conditions. So for the LiDARs, that's clouds. Weather like that out there is not very good because they get light scattered back from the clouds, very, very strong scattering, and that basically gets rid of the signal. In our case, we've got problems whenever there's too much noise out there because it's an acoustic method, very audible, so it's beeping at frequencies of 2000 hertz, which sounds something like kind of thing. And so any tractor, any birds in the shrub next door can be a possible problem if they're chirping along too long. Usually not that big of a problem, but there are data availability problems. And so what we are doing with that new project, and I've taken a long time to get there, is we're trying to make these SODAR measurements better. And the way we are trying to do that is we're trying to implement more sophisticated digital signal processing. And Paul, the postdoc who is working on that, is the expert on that, and he's a very, very good guy. And he's made tremendous progress in trying to simulate the atmosphere so far. So he's been working on the project for a year. And what we are doing in that project is we're first trying to simulate what would happen if we implemented more sophisticated transmit signals. So I've given you an example of a very, very simple transmit signal, just a sine wave, very short pulse. What we are going to do in the first instance is we're going to have a series of different frequency pulses, because that is the most promising approach. What we could be looking at to get really nice high spatial resolutions would be to use very, very sophisticated pulses. But that works very, very well in radar technologies, so electromagnetic scattering technologies, and it probably won't work for acoustic technologies. And there are good reasons, physical reasons for that.
As we can see here, the y-axis here is height, and this is just distance along the ground. So it's just a two-dimensional model. It's like a slice of the atmosphere, and we can see this kind of this messy kind of porridge that we can see here is basically just the how the temperature changes with height, and we can see it changes fairly randomly. And this is meant to model turbulence. But what you can also see is it's shifting. And what I've done is I've tried to model wind in a way. So the wind is pushing these turbules along, and we can see here it's moving faster at the top than it is here at the bottom, which is the general case in the atmosphere. The wind is a lot faster higher up than it is right on the ground.
What you've got in the air is you've got something that we call eddies, whirls. So you've got rotating structures. Now they're not exactly like a ball, circular, rotating, but what they are, they're completely random. We know that as gusts, we feel that as gusts, but there are these types of moving structures in all kinds of sizes, down to these little sizes up to a few hundred of meters.
I'm basically trying to simulate how a real SODAR works, and I've got a sound source in this bottom left corner here, which is sending out a single frequency pulse. It's a finite pulse, so the pulse has stopped now, so we can see it's propagating vertically. We could ignore the horizontal propagation, but what we can see is as it travels over those random fluctuations in temperature, we can see that we're actually getting sound backscattered from those fluctuations.
So what we have to do to get a wind direction and speed is we have to measure in more than one direction. So we measure in the vertical, we tilt the beam over, measure in that direction, and we tilt the beam in another direction, and we measure in that direction. And that gives us a composite wind vector. Slight problems with that, of course, you measure in 3 different volumes. So if you're measuring over a hill, where the flow is very exaggerated, concave or convex or whatever, then this volume would not see the same flow conditions as this volume would do. And that's the same problem for both SODARs and LiDARs. And the way to get around that would be to design a system that has got a sender here, a receiver there, and they are looking at a column of air, a common column of air. And what you need in that case is you need 1 transmitter and you need 3 receivers to get the 3 directions. And these types of systems are prototyped in New Zealand currently in a project that is actually led by Salford.